Have you ever stopped to think how the tiny chips inside, well, everything, your phone, your watch, can be so incredibly fast and power efficient? Well, today we're going to pull back the curtain on one of their cleverest secrets, a design trick that really makes it all possible. Okay, let's get into it. Right, so it all boils down to this single question. We live in a world where our devices are constantly gathering data, right? Your watch is tracking your heart rate, your phone knows the weather. How do they process all of that information without just completely draining the battery in minutes? The answer is, well, it's really clever. It's all about working smarter, not harder. To really get our heads around this, let's picture something. Imagine a small embedded device sitting out in a field somewhere. Its whole job is to monitor the environment. This little guy is the perfect example of the kinds of challenges these tiny chips are up against every single second. So, inside our little monitor, there are sensors constantly checking the temperature, the humidity, and the air pressure. And all that data gets stored in the chip's memory, all lined up nice and neat, one right after the other. So you got temperature at memory address 9000, then humidity right after it at 9004, and pressure at 9008. And here is our challenge. For a little gadget running on a battery, every single instruction the processor runs uses up a tiny bit of power and a tiny bit of time. So the name of the game is efficiency. We have to grab all three of these values using the absolute minimum number of steps. Now, before we can solve this puzzle, we got to understand one fundamental rule about how these super efficient ARM processors deal with memory. It's called a load-store architecture. Now that sounds a bit technical, but the idea is actually super simple. Think of it like this. The processor can't work on data when it's just sitting out in the main memory. It has to first load the data onto its workbench, a tiny, lightning-fast storage spot called a register. Once it's done tinkering, it can then store the result back into memory. And the tools for this job are pretty straightforward. LDR is for load register, which pulls data in, and STR, you guessed it, store register, which sends data back out. These two commands are basically the only doors between the processor's workspace and the big memory warehouse.
Now, the engineers at ARM are smart. They knew that this task, grabbing a bunch of data that's all lined up in a row, happens all the time. So they built in some incredibly clever shortcuts right into the chip itself. You can think of them as smart pointer techniques that just make everything faster.
Okay, here are the three main tricks they came up with. The key thing to notice here is that last column, base register update. But more importantly, look at the one on the bottom, post index. See how it calculates the address after it accesses the data? It grabs what it needs first, then it automatically updates the pointer for you. That little detail, that's our secret weapon. And yep, for our little environmental sensor, this post-indexed addressing mode is the absolute perfect tool for the job. It lets us read a piece of data, and in the same breath, get ready for the very next one. All right, enough talk. Let's actually see this solution in action, step by step. You're gonna love how clean and simple this is. Here we go. Step 1. We use this single instruction. It tells the processor, hey, see that pointer, R1? Grab the data from the address it's pointing to and stick it into register R0. Right now, that's our temperature. But here's the magic. That little comma and number 4 at the end, that tells the processor, oh, and after you do that, add 4 to the pointer for me. So bam, one move, 2 jobs done. The data is loaded and the pointer is already aiming at the next piece of data. On to step 2. We do the exact same thing again, just for a different register. The processor looks at the pointer, which is already in the right spot for humidity, grabs the data, and boom, automatically moves the pointer to the next location. It's like clockwork. And the final piece, pressure. One more time, we run that same beautiful instruction. It grabs the pressure reading, and just like that, the pointer is instantly updated and is now sitting there ready to go for the next time we need to read all the sensors. So clean. And there you have it. Just take that in for a second. 3 simple instructions, and not only have we loaded all of our data, but our pointer is perfectly positioned for the next round. There are 0 wasted instructions, which means 0 wasted energy. And this right here, this is the real aha moment. On the left, you see the old, inefficient way. You'd need one instruction to load the data, and then a whole second instruction just to move the pointer. But with the ARM way on the right, it's all baked into one powerful command. We are literally cutting the amount of work in half. And when you're doing this millions of times, that's a massive saving. So okay, we saved a few instructions. Who cares, right? Well, it turns out this tiny, low-level detail has huge implications for all of us. Think about it like this.
Every instruction your phone runs takes a tiny sip of battery power and a tiny slice of time. But your devices are doing these things millions, even billions of times a day. All those tiny savings add up to the things we actually care about: longer battery life and a device that feels snappy and responsive.
And this isn't just some academic trick. This exact technique is the workhorse running behind the scenes in so many critical systems. We're talking about everything from smart IoT devices and medical monitors to really complex stuff like radar and image processing. They all rely on this kind of extreme efficiency to even work at all.
This quote just sums it up perfectly. These addressing modes are a specialized tool built for one purpose: to fly through blocks of memory, just like our sensor data, using the absolute fewest instructions possible. It's just a masterclass in elegant, efficient design.
It really makes you wonder, doesn't it? What other brilliant, hidden gems of design like this are buried deep inside the technology we use every single day, silently and efficiently making our entire digital world possible?